In this example, we're going to start to investigate the ideas behind common factors and the greatest common factor. So we haven't defined these terms yet, but we're going to build them up by looking at this problem. I challenge you to try to work on this problem on your own and figure it out, and then come back to the video and see what the results in the video are. It will really help to give you a good idea of these concepts. So let's go ahead and read the question. Scottsdale Community College wants to paint one of their walls in the Student Center with different colored squares. The wall is 12 feet by 18 feet. Here's our question. What are the dimensions of the largest square they can use so there are only whole squares painted? There's another question. Are there any other square sizes that will work? Explain. So let's take a look at this problem. Here we have a grid ready for us, and it's 12 feet by 18 feet. Remember, the grid marks off at tens, so this is 10, 11, 12, so let's put a 12 here. And here we have 10, and then 8 more going this way for 18 feet. So we can think of this as our wall, okay, where each unit of these little squares is 1 foot. Any square inside it, little square, would be 1 square foot. So we want to paint only whole squares. So let's look at a couple of examples just to get started, one that will work and one that won't work. So I see an example of a square size that absolutely won't work. So say I decided to make my squares 10 by 10. Well, this is 10 by 10. So this would be 1 square. You get the gist. But notice we have these other pieces, but we couldn't make whole squares out of them. This would be 10 units long this way, but we could only go 8 to the right. We'd need to go 2 more to get a 10 by 10 square. Down here, we could go 10 this way, but we'd only have 2 this way. We'd have to go 8 more, which goes off the page, to get a full square. And a similar idea here, except we'd only have 8 and 2. So that means 10 by 10 squares do not work. But 10 by 10 is a no. So now let's try to think of some other numbers that we can check. So let's just take a look at 12. Well, I know that I could break 12 into pieces of size 2. So there would be a size 2. I'm just going to make squares going down. So I'm going to go down 2, and there's a square that's 2 by 2. Here's another one. And I'm going to keep going until I get to the bottom. So on this left-hand side, if I go down 2 units at a time to make 2 by 2 squares, I get 1, 2, 3, 4, 5, 6 squares. Well, that makes sense because 2 times 6 equals 12. So if I divide the 12 by 2, I will get exactly 6 squares going downward. But now, is this going to work in the other direction, or is something going to get cut off like we did with the 10 by 10? So let's take a look. Well, I could keep making 2 by 2 squares. And as I keep going, I'm wondering if I get to the end, will they all be filled in? And we're almost done. And this did fit. We didn't go over or under. And we had 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I broke the 18 into 2 foot by 2 foot squares, I had 9. So 2 times 9 equals 18. Or when I divided the 18 into 2 equal pieces, I got 9. So you can imagine, I won't draw them all out and make you suffer, that I could continue drawing these 2 by 2 squares all along in rows and down in columns, and it would fill it up exactly. Okay? And it looks like the reasoning is since both 18 and 12 can be divided by 2 without a remainder, they'll both go to these borders without any squares left over for them to fill. So 2 by 2 is a yes. So now we know one no number and one yes number. And if we think about the 10, well, we divided 18 by 10. That would be 1 with a remainder of 8, so we wouldn't be able to do 10 by 10 squares this way. 12 divided by 10, well, that would be 1 with a remainder of 2, so we couldn't break 12 into exactly pieces of size 10. So let's try to think of some other ones that might work. Well, I'm going to look at 12 and 18. So I know 12 I can break into 1 and 12 pieces. I can break it into 2 times 6 pieces, or 3 times 4 pieces. And at this point I'd stop. If I went on to 4, I'd just get the remaining factor pairs. With 18, I could do 1 times 18 pieces, 2 times 9 pieces, 3 times 6 pieces. 4 does not go into 18. It goes in 4 times with a remainder of 2, but it's not a factor, and neither does 5. So these are all the factors, or the factor pairs of 12 and 18. Now notice they both had 2 as a factor, and that's why we were able to fill in the squares this way. Let's see what other factors they have in common. Well, they both have 1, and they both have 3. And let's see, 12 has 4, but 18 doesn't. 12 has 6, and so does 18. And 12 has 12, but 18 doesn't, and the same with 9 and 18. So these were their common factors. I'm going to make this one blue. So their common factors were 1, 2, 3, and 6. Okay? So we could make squares with these dimensions, 1 by 1, 2 by 2, 3 by 3, or 6 by 6 squares, and it would fit exactly. We wouldn't have any partial squares because we wanted only whole squares painted. Now the largest number would be the largest common factor, which is 6. So let's take a look at this. So 1, 2, 3, 4, 5, 6. Oh, I went over too far. Shoot. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this would be one square. This would be another square. There's another. And there'd be corresponding squares underneath. So 6 by 6 are the largest squares that we could make, so that we only use whole squares painted.